Thanks for the organizer for letting me give you a talk today instead of yesterday. So I've been called today a couple of times the SETI guy, so that kind of tells me that I cannot give you any details. But any specifics that you have, I can happily answer for you during the question session or later. All right, so I'm finishing my PhD in the Netherlands, and I'm moving to Berkeley to do my postdoc part of this group, the breakthrough listening group. So we'll tell you today about the search for intelligent life outside the Earth, if we actually have here some. Anyways, so this is my kind of introduction. I have 3 parts for this talk. So I'm going to give you some introduction of SETI. I'll tell you about the breakthrough listen project that I'm part of. And also I want to tell you about a little bit of other things that I'm interested in, which are also part of astrobiology, which kind of ties into with other stuff as well. Okay, so what is SETI? SETI stands for the Search for Extraterrestrial Intelligence. And kind of way to think about it is, so you have astrobiology here, and you have communication technology of many kinds, and kind of SETI is kind of somewhere there. I'd like to start this introduction by asking a question. And this is, how common is intelligent life in our galaxy? Of course, nobody knows the answer to that. But you probably have seen this before. This is the Drake equation. And instead of an equation, it's more of a guide to help you think about this question. So what kind of ingredients you need, or what are the requirements to have intelligent life somewhere else that we can actually detect. So you have, I'm just going to go into the next slide. So the first 2 parameters you have here, it's how many of the stars from our Milky Way, how many of those, what is the fraction of those that have planets? And of those, what is the fraction that you have a planet in what is called a habitable zone? So you can actually have life there. So from Kepler, we know that basically every star out there, when you look at the night sky, every star you see has a planet, most likely. And we also see that there are lots of them that have planets in the habitable zone. So you have your star here, you have a red area, which is too warm to be, the blue area to be, which is too cold, and the green where it's perfect to have liquid water, basically. So then we can see that these 2 terms are hinting to have, are telling us that all these 2 are common. But what about the other parameters in this equation? So you have, out of the fraction of planets that you have around that are in a habitable zone, how many of those actually have life? How many of those will create intelligent life? How many of those actually create a civilization? And L stands for the length of that civilization. So let's start to think a little bit about that. So I'm glad that I actually gave the talk today and not yesterday, because, well, we have covered a little bit of this today. And so there are some hints that maybe life, well, I guess the building blocks of life might be out there everywhere. We also know that life seems to be very resilient here on Earth. And given cosmological times, we can think, well, we have probably enough time to evolve into something that is intelligent. But at the end, we don't really have any constraints on this. We don't really know. So what you can say is that at the end of the day, it's equally likely, completely equally likely, that we are the only civilization in the galaxy, or there are thousands of them. We just don't know. But as Carl Sagan said, and we don't really have models to do this, right? So the only way that we can figure this out is by making an experiment. So in SETI, when you're looking for intelligent life, you're not looking for pretty smart dolphins or chimpanzees. What you're looking for is for technology. And we're using technology as a proxy for intelligence. So in this case, these are examples of that. So specifically in technology, I mean using what we use for communication, which is the electromagnetic spectrum. So we have radio antennas or radars, but also we have lasers, right? And so all these are possibilities that you can basically communicate through space. And from the surface of the Earth, so this plot right here shows basically wavelength, the opacity of the atmosphere. So you can see there are some windows here where we actually can observe what is out there. So this is the optical. We can see the stars with your eyes. But you can also have radio and infrared. So at this moment, most of the SETI work has been done in the radio, but there are actually a few that has been done, especially in the optical, and a few that are starting to do in the infrared. So I just want to show you a little bit video here to help us think about these SETI ideas and how to find civilization out there. So imagine this is the galaxy, this is the Milky Way. So imagine you have a planet somewhere which is in the right spot. You have it there. It has life. It creates intelligent life. It creates technology, and it starts sending radio signals. Then at some point, it might just die off. What you will see then in the galaxy is that you'll have these bubbles of radiation, of electromagnetic radiation. And here on Earth, that's where we are right now. We're emitting, and hopefully we will still be emitting for a long time. And at some point, you will start receiving the signal from all these bubbles out there. And I guess going back to this picture, you can see that the thickness of these bubbles basically reflect the length of this civilization, for how long they have lived, and basically this tells you that at some point they became extinct. So I think this is very relevant currently for our state of our own civilization. It's something to keep in mind, right? And I guess the other thing that I want to show here is that, so Earth should be somewhere there. And maybe you can see that it's like a point, or maybe the laser. So that will tell you the extent for which we have conducted SETI experiments. So we have only searched stars which will be around that laser. So there's lots of stars to search for. So what kind of signals are we looking for? So this is actually a real signal, artificial signal, that is coming from outside the solar system. I know that it's artificial because you have frequency here, this is radio, and you have these very strong lines here. It's artificial because they are very narrow. Nature doesn't know how to produce these kind of lines. Masers are the narrowest kind of things that nature could produce, and those are thousands of times wider than this. So I know that this is artificial. Unfortunately, I know too that it's the Voyager 1 spacecraft. So it's terrestrial, I mean, man-made, I guess. But this kind of gives you an example of what kind of signatures are we looking for in our data. We're doing this, well, actually, to give you an example, so how sensitive we are, Voyager has a 40-watt transmitter, sorry. So basically the same, the light bulb in your fridge. And we are able to detect that, even though it's outside the solar system now, very strongly with this telescope, which is actually very close from here. It's a Green Bank telescope, and some of you this weekend probably saw it. And just for reference, you can see the size of the trees nearby. It's pretty large, the largest of this kind. So kind of looking at the future then. So here, this plot, you have a wavelength or frequency, whatever you want. And this basically tells you the sensitivity. And the green line here tells you about GBT, the Green Bank telescope. And these are basically our telescopes. This line right here, the dotted line, that represents the strongest transmitter, radio transmitter that we have currently, which is the Arecibo planetary radar. So if you put that at a distance of 50 light years, you can detect it now. In the future, with the SKA, the square kilometer array, you will be able to detect much fainter signals. like basically a radar from an airport. It's kind of a little video here. I'll just skip through. So this is the Sky Kilometer Array. And basically the idea here is that once in a couple of years, once this is finished building, we will be sensitive enough to have, for the first time, enough sensitivity to look at a large volume of stars and to start to answer this question in a very statistical way. So I'm very excited about that, and stay tuned for that. Okay, that's kind of finishing my introduction here. So as I was saying before, SETI is a search for extraterrestrial intelligence. And usually people confuse SETI with the SETI Institute, which is very famous, but it's not it. I'm part of what is called the Berkeley SETI Research Center at UC Berkeley. And there are other SETI institutions out there, much smaller, but well, there's still a bunch of people. In general, it's a small field. This is a group in Berkeley. Something that you can see right away is that we need half of the population that is not contributing to this work. So please come and join us. Men cannot do it by themselves. Okay, so now I'm going to tell you about the Breakthrough Listen. This is a project that I started a couple of years ago by the contribution of $100 million for spread of 10 years. This is the largest project ever. This is Yuri Milner. He was the one that contributed for this. You can see some famous people here. This is Frank Drake, actually, which is from the Drake equation. And you can see how large this project is just by looking at the number of people in the board of advisors. These all were well-known scientists. So very basically, what I can tell you is that we're using the most sensitive radio telescopes in the world at the moment. So the Greenman telescope for the northern hemisphere and the Parkes telescope for the southern hemisphere at the moment. We're hopefully adding more telescopes in the future, but stay tuned. Quickly, I'll tell you that so this project has lots of sub-projects in between, in the middle. I guess we're in the future, we want to observe nearby galaxies as well as the plane of the Milky Way. For now, we're concentrating on a set of targets of the closest stars. So for that, we just submitted a paper a couple months ago on the first observations for the first year, where we concentrate on a subset of frequencies here between 1 and 2 gigahertz, where we were looking at 700 stars. All of them are nearby. They are spread all over the northern hemisphere. And I guess one difference from our work than other earlier SETI experiments is that they were concentrating their efforts earlier on only solar-type stars because we didn't know better. But now we know that planets basically can exist in all kinds of stars, and they all have an habitable zone. So trying to remove the anthropocentric point of view as much as possible, we're then observing all kinds of stars. Very quickly, I'll tell you that we have a lot of data. We constructed a lot. These are hundreds of computers that we're using here at the Green-Bag Observatory. And without going much to the results, we basically found some interesting candidates, but at the end, we figured out those were from nearby satellites. So, but if you don't like my conclusion that we didn't find ET, there are lots of other conclusions that you can find online from this is worthless, you guys doing, and you actually find ET. But choose your best, your preferred option. Just kind of to finalize, some other way that you can use this data. I mean, we're observing a bunch of stars, and stars tend to do crazy things. So this is the sun here. This is what is called well, basically a flare from the star, from the sun. You can see this is the white circle represents the size of the sun. So you can see how much bigger this is. This also emits in the radio, and we can detect that. Also, Jupiter here has aurora, which also emits in the radio, and we can detect that. Some work now has been detecting radio emission from other stars and brown dwarfs as well. So the reason why this is important is because, so we know, as I was saying earlier, this is the habitable zone, this green here shape, and depending on the size of the planet, of the star, the larger the star, the more bright you are, and the more, the hotter you are, so the habitable zone kind of moves away from that star. But this is not the end of the story, right? So also what you need, as we have here on Earth, it seems that you need a magnetic field surrounding your planet to protect you from crazy things coming from your host star. So that's something that we also want to do with this data in the future. So maybe next year I'll tell you more about this. There are a lot of things that I didn't tell you about from the Breakthrough Listen initiative. We have an RU program, so if you have any undergrads interested in this, please let me know. And yeah, many other things, but you can always ask me questions, or you can also go to our website. And we actually have a monthly collaborative meeting where we basically gathering a lot of people. It's happening tonight at 2 a.m. We're kind of shifting schedules so like everyone from the world can join. But yeah, if you're awake and not too intoxicated, maybe you want to join. Yeah, thanks.
All right, got time for one question.
Hi, I was wondering if you could give some feedback of what your opinion might be about the WOW signal some decades ago, and also Tabby star.
Right. Yeah, very interesting things. So the WOW signal, I haven't looked very deep on it, but what I can tell you is that most of the SETI community at the moment don't believe that is, most of the SETI community don't believe that is a real signal. The reason was that, without going too much into details, you were observing I don't know if you're a radio astronomer or not, if this will make sense or not, but basically the signal, even though appeared once, they never saw it again. Not even in a following observation, basically a few minutes later. So there is a lot of, once you find a signal, you really want to find it again and again. And not just with one telescope, with multiple telescopes. And then you can start believing that this comes from actually that location. Otherwise, there are so many what we call radio frequency interference coming from Earth that it is very hard to remove otherwise. About Tabby star, we actually have been doing observations of that. So for those who don't know what Tabby star is, so this is a very interesting star, which I wish I have time to talk to you about it, which deserves a full talk. But it was discovered by Kepler, and it has very strong tips on their brightness. And usually these tips are related to planets going in front of the stars. But in this case, these tips are very large, and they're very weird. They're not the usual type. So astronomers have been scratching their heads for more than a year, really trying to figure out where this is coming from. Still under heavy debate. There has been a very recent event, another dip happening basically 2 weeks, well, last weekend, the weekend before that. So it is right now it's a very hot topic. A lot of telescopes were just directly looking at it. So I expect many news in the next following weeks on this. So yeah.
All right, let's thank our speaker one last time.